He's going to be talking about new interface development in the AMPL modeling language and system. And let me just give a little bit of a biography background on Bob. You know, he's been working in optimization since the 1970s, and he started at the National Bureau of Economic Research, and he studied operations research at Stanford University. A member of the Industrial Engineering Management Sciences faculty at Northwestern University for 3 decades. That's pretty impressive. And during that time, you know, worked with David Gay and others on the AMPL modeling language while on sabbatical at Bell Laboratories. And then in 2002, he co-founded AMPL Optimization Incorporated to advance the AMPL system. And one of the reasons why we wanted to have Bob present today is they've been making some very nice progress on AMPL. It definitely has a huge user base, and they're continuing to improve it with additional solvers, or as we'll see today, some new interfaces, integrated development environment that he's going to be sharing with us.
You've seen the title there, and what I try to do is give a talk that is sort of give you an idea of issues in modeling languages, and I try to make it not just a sort of an ad for AMPL. Let me say that when it's to talk about interfaces, and really the whole idea of algebraic modeling language was to be an interface. It was to deal with the problem that it was so hard to get your problem into the solvers that were supposed to solve the problem and to get your results out. And so initially it was an interface to solvers. You wrote your models in this algebraic form, which is much more natural to you. And then the computer translated to and from the data structures that different kinds of solvers required. And but what happened was, back a bit here, what happened was that once those modeling languages got developed, then people started having demands for interfaces to the modeling language system. So the interface problem was not solved, and users wanted better interfaces. So they wanted things that were more interactive and that sort of integrated their experience better, so that they could more easily develop models. And then there was the whole issue of applications and how this modeling system was then going to interface to the rest of the world. And so there became a demand for things like scripting languages to build applications and even more ambitious application programming interfaces and even development environments. And so in this talk, I'm going to touch on almost all of these things. The only thing I won't say a whole lot about is the really full-blown development environments to let you build an application from scratch. Those are things like AIMS and IBM's ODM, and those are things we haven't really attempted in AMPL. But I'm going to go through pretty much all the other things and show how they developed and how people use them, and what we're developing that's new. So then, just to get started, I'm going to show a number of AMPL examples, and my intention is not to really explain all the lines in the examples, but just to point at specific things. And so like at the beginning of an AMPL model, what I want to say is that you define various sets and parameters are usually, really arrays indexed over various sets and so forth. And this thing is from a staff scheduling problem that'll pop up in a few places as an example. And once you define your data as sets of parameters, then you define your model. And so we have some variables. There's a variable number of people who work each schedule, and there's a typical of an integer program. There's a 0, 1 variable that's 1 if and only if a schedule is used. And there's an objective here, and there's some constraints that you have to meet the requirements, and there's some typical things you see in integer programs. There's some fancy linear constraints that constrain each schedule to be used at least a certain minimum number of times if you use it at all. And so there's like a model, okay? Variables, objective, constraints. And the thing about modeling languages is all this is symbolic. Okay? You don't actually see any data there. Instead, the data is in some separate place. And here's part of the file with all the data, defines all the shifts and what days are in the shifts and how many schedules there are, what the requirements are, and then the idea is the solvers are independent of the model and data. So So here I read in the model and the data, I say at least 7 people have to be assigned to every schedule. If you use that schedule, I select the solver, and the solver goes. And so the solver is not built into the modeling language. It's a separate thing that can be called. You see here I've displayed the results. And here already you see one interface. This is actually when we started out AMPL long ago, the idea of having an interactive interface of any kind, just one you could type commands at, was a big deal. I mean, that you could sort of wait and solve the problem and then just decide what to display. Here I just display some variables, but you can look at any values you want. You can change things and you know, troubleshoot your model and so forth. And here you see some results. So here's a simple command line interface that was already a big deal when we started. And now, if I wanted to use a different solver, I can just, you know, pick a different one and I get a different solution. And you'll see there are lots of solutions to this problem actually. And so here's an outline then of what I'm going to do. I'm going to first talk about interfaces for developing models. And first I'm going to look at just the interfaces that are in the modeling language. So if we can improve the naturalness of the formulations in the modeling language, we have a better interface just through that. So I'm going to talk about a couple of different things, just show some examples of that. And then I'll talk about development environments. And these are environments that help you work with the modeling language. So they don't actually change the language, they just put a frame around it. And I'll describe 2 of those that are in current development. And then second, I'll talk about interfaces for deploying models. And first, the simple idea of scripting, which is widely used with AMPL, which is to extend the modeling in the command language to something you can write little sorts of programs in and actually build up an application. And then I'll talk about something more ambitious that we're doing now, which is to wrap the AMPL system in an application programming interface and let you access it through programming languages in which your actual application might be developed already. So that's the outline of the things I want to cover. And so first I'll talk about more natural formulations. And that's the idea of a better interface to the solver by bringing the modeling language closer to the user's conception than just these algebraic statements, and let the translation do more of the work. And so I'll first talk about logical conditions. These are things like either/ors that are not purely algebraic, okay? And show various solver strategies for those. And then I'll say a bit about quadratic constraints, which is something that's come up in recent years, where it turns out that there are the modeling language can prepare things and recognize them as quadratic and enable various solvers to handle them. So then, okay, so we'll start with logical conditions. I'm going to do a series of 3 examples. So here's a multi-commodity problem. It's just you know, least cost way of shipping from various origins to various destinations of various commodities. But we say that what makes it complicated is from each origin to each destination, you have to ship at least a minimum amount of all the commodities, or else nothing. So that's the sort of complicating constraint in this here. And so we have some variables that are the amount to ship from each origin to each destination of each product, and we have some of these 0/1 variables that are 1 if you ship anything and 0 if not. And what I've shown here are the 2 constraints you would put in. That the usual integer programming trick to relate the use and the trans variables to say that, well, if I use a certain origin destination pair, then I ship between the minimum and the maximum amount. And if I don't use it, I don't ship anything. And so this is typically how we tell people to formulate this. And if you've done a lot of integer programming, you can convince yourself that this is a natural formulation. But I would argue that, in fact, this is a trick, and if you haven't learned the trick, it looks pretty crazy. And the great thing is it's linear, so I can send it to C-PLEX or Gurobi or whatever. Now, what we could do is make the language more natural by saying, this implication, we could say, look, if use ij is 1, then the amount shipped has to be between some minimum and this limit on the shipments. Otherwise, it should be 0. That's certainly a lot clearer. It says what I told you originally. I wouldn't have had to describe it if I had this. I could have just pointed to the AMPL. Now, it turns out that AMPL will recognize this, And if I send it to C-PLEX, it'll solve it. Okay? So I don't know how widely known it is, but this is called a C-PLEX indicator constraint. As long as the thing on the left side of the implies is the 0, 1 variable equals 1 or equals 0, implying something, then it'll just take it. And there's behind the scenes, AMPL recognizes that this is a proper sort of constraint to pass to C-PLEX. It figures out that there's a condition here and a constraint there, and does all this work behind the scenes. Okay, and so there's one way that we can improve the interface. Okay, is just by allowing that. Now we could go even further than that and get rid of the 0, 1 variable. So here's an alternative without 0, 1, and that is, why not just say that either nothing is shipped or the shipments are between this and this. I mean, those 0, 1 variables only seem natural because we're so used to writing integer programs. But if you're not used to it, then I think this seems a lot more natural. It's what I said originally. You ship nothing, or you have to ship between these limits. Okay? And can I solve that by C-PLEX? Well, not if I use our usual C-PLEX interface. It'll say, that's not an indicator constraint. It's a logical constraint, has an OR in it, but it's not an indicator constraint. However, there's a backdoor. We did an interface for IBM's other solver, what's called their constraint programming solver, which I'll say a little more about in a moment. And it turns out when you use the interface, interface to that solver, there's a backdoor into C-PLEX as well. And the constraint programming solver, it turns out, it can deal with this OR. And if you send that to C-PLEX, it will translate it. So if I use this so-called ILOC-CP solver, but I tell it to really send it to C-PLEX, then it turns out it will translate that. So it turns out there's this feature which is sort of hidden in C-PLEX, and I don't think it's much used, that if you want to write disjunctive constraints, it will translate them to something and solve them. And people might argue that if you translate it by hand to a linear thing, you could do a better job. But then again, I'm not sure. You might do a worse job. So this is something I'd like to see more of. If you just write the logic that you have and let it be translated, and you know, say what you have in the modeling language what you have in your head, which is the whole idea of modeling language. Okay. So now, what about this ILOC-CP? Okay, that actually can handle much more general sorts of constraints. So I made up this example where you optimally order. It's just the idea is you have this collection of jobs and a set of adjacency preferences, and you want to satisfy as many as possible. And your decision variables are, there's these variables that are 1 if and only if a certain pair is actually adjacent. So this tells me how many of the adjacency requirements are satisfied. And there's a variable that says, called pos I, and that's the position of job I in the sequence. This is very different from the kind of integer programming formulation. Not a 0, 1 variable. It's a position valued variable. The value of this variable is the position of the ith job. So compared to what I would do with 0, 1 variables, there are a lot fewer variables, but they have larger domains. Now, what can I write with these variables? Well, I could write something like this. The requirement that there's only 1 job in each position, I can say all the pos i's have to be different. I use this all diff operator, and then to say that the satisfiability variables relate to the position variables, I just say that an adjacency requirement is satisfied if the positions differ by at most 1. And then I have this little symmetry breaking thing in here that just, I mean, you can always flip the order, sort of reverse the order of everything, and you get an equivalent solution, so that breaks the symmetry. And so this has constraints that are really different from what you see in like integer programming where you need linear constraints, but there are solvers that can handle them. And so you see here I've run the ILOC-CP solver, and it solves it in here. We hooked it up to another one called G-code that solves it as well. And so in making the language a more expressive interface, we can also look for supporting solvers that are more capable. And so currently we support all these things, and we support these solvers as well. Okay, I won't say too much about that. You've seen these all diff and so forth. And but let me say what we'd like to do is do some automatic transformation so that if you have some linear solver maybe our interface would do this transformation for you instead of relying on the solver to do it. And we'd like to recognize some new forms like variables that take values in sets of objects, and then this thing where you can have inside the subscripts of a parameter you can have variables, and maybe even set membership requirements that say, well, this pair of variables has to be in the set. And so we're looking to further expand the syntax actually to make it possible to say more things naturally. Okay. And
Bob, I just had a question for you on that.
Yeah.
You know, you mentioned C-PLEX has a few unique features that allow somebody to pose a problem in a certain way.
Right.
Do you find that because C-PLEX supports that form that other solvers like the Roby or others are, they kind of are working to also make that standard in their software as well? Or how much of an AMPL model would you say is somewhat solver specific versus solver generic?
Yeah. Well, a lot depends how you write it. I think if you write things in linear or sort of continuous nonlinear form, then it's very solver generic. And but if you start writing this logic, then I find that it breaks up, and to a lesser extent with the quadratics as well. That then it depends what the solver recognizes and what we've done. And I guess I'd like the solver vendors to move more to accept, recognizing more things. But I think also maybe we need to make our interfaces more solver generic, and so that if the solver doesn't recognize it, we translate it to something that it does.
Right, because I see that as one of the powerful things of AMPL is that you can pose a model and then switch between solvers if one is working better than the other. But there might be some reformulations that the user can do to disjunctions or other things that you mentioned. They can still solve them, but they may have to just reformulate them.
Yeah. Actually, reformulating disjunctions is a real nuisance. It's the most commonly asked formulation question is, how can I linearize this? And I really think that the systems could do a better job of helping people with that and freeing them of the trouble.
Okay.
And so let me briefly say, I'm going to skip a few slides here in the interest of time and say, I won't show the actual formulation of this traffic flow problem. I'm going to show the AMPL. And I just want to do this to show quadratic things. It has variables that are the flow in cars per minute along various roads and the travel times. And the idea is to minimize the average time to get through the network. And the thing is, there's this very nonlinear constraint that relates the travel time to the flow. And basically, it blows up as the flow approaches the capacity. Okay? And if you try to solve this problem with some little data here and send it to a general nonlinear solver, it'll at least tell you you've got a locally optimal solution. And so I've done it here with Nitro. And if you want to make the flows integer, even then Nitro will solve it, give you some integer flows and tell you it's a locally optimal solution. But it turns out you can use, you don't need a nonlinear solver to solve this problem, actually. And if you just try to solve it directly by using, say, Roby, it'll throw you out and say, well, I can't handle these nonlinear constraints. But notice it says non-quadratic. And if you look back at this problem, if I substitute time, this time variable, into here, I get something that looks like a squared term over a linear. And if I define a variable equal to that and then put in a constraint, it turns out I can reformulate this as the following, as just a linear plus this variable delay, where delay satisfies this. So it's just a simple, real algebraic substitution. If I write, this is an entirely equivalent problem, and now it's got quadratic on the left and quadratic on the right. So now Roby's complaint that it's non-quadratic has been relieved, okay, if you know how to do this. Okay? It didn't look like it was quadratic, but now if I try to do that with Roby, it'll say it's not positive definite, right? It's complaining it's not. And here's a case where if you only knew that Roby recognizes some quadratics and not others, you would know that you should take this, what I call the slack, and you should replace that with a single variable. So I'm going to rewrite it like this, replace that with a single variable equal to this thing, with this term which used to be up here. And now it turns out this special kind of quadratic, a square on the left and the product of two non-negatives on the right, is recognized by Gurobi as a second-order cone, which is actually convex. So this is now recognized a convex quadratic problem, and Gurobi solved it. So here's a case where if you only know how to write it the right way, it'll solve it. And furthermore, somehow automatically when I write it this way, it's recognized as being solvable. And so suddenly my interface enables me to do something I couldn't do before. Okay, and it'll solve it as integer 2. And so currently, certain quadratic problem types are recognized, sort of elliptic ones and conic ones. And AMPL recognizes these things, multiplies out linear terms, forms quadratic, sends all the linear and quadratic coefficient lists to the solver. And then the solver will recognize certain things. C-PLEX and Gurobi will detect elliptic forms numerically by looking for positive definite matrices, and conic forms by looking for certain structures. Okay? But what we'd really like to do, and I think this gets back to the question that you asked, is we'd really like to recognize the original formulation and automatically transform it to whatever particular solver needs. And in fact, we have some prototypes of this that I did some work with a graduate student for his thesis where he figured out ways of recognizing and automatically transforming all sorts of problems that work this way. Sums of norms, squares divided by linear, that's the example you saw, various generalizations of geometric means and p-norms and so forth. And so again, what we're looking to do is to make things more solver independent by putting more recognition into the interfaces and building up a library of recognizers. And I think that's something that you'll see in the next year or so, is more of these things being recognized. Okay. So now I want to move on to development environments. So now let's step back from the language and ask, what about using the language? And people have been trying to do development environments for AMPL for a long time. It seems every 10 years a new one comes along, and but always the idea was to sort of integrate all the modeling activities and not make it seem so fussy, where you had to have an editor window here and you had to type all these commands here and so forth. And the previous attempts, however, I felt they went too far. They tried to get rid of the commands entirely, and or at least minimize their use and put in all these menus. And the result was that lots of people who were already comfortable with using it didn't want to switch. And it just sort of created this new camp of some users who were doing things differently. And the other thing I think it didn't work is that the command form of running things actually has never gone away and has a certain value to it. In fact, its popularity has sort of been returning. You look at languages like R and Python and MATLAB, and they're actually command-based. Okay? And you really have to see the commands you've typed to know where you are in your session. So what we've done recently is create this AMPL IDE, which is just a simple independent application that integrates the editing and the command line. And the idea is to eventually make it more complicated, but to first bring people along to this simple thing. At the same time, there's been development of an Excel-based platform that supports AMPL and various other languages that I'll mention briefly, called Solver Studio, if you want to see something that looks really different. Okay? So let me say something about the IDE. So it unifies, like I said, the editor and the command processor, and it gives you an easy upgrade path. It doesn't replace the command line version if you need it. It's built on Eclipse, and works with all the existing implementations. Now here's a screenshot of it, but rather than give you a screenshot, let me just show it here briefly. The idea is you fire this thing up, and instead of just getting a window facing you with command, it gives you a few windows. And if I go over here, I can find some files. So here in my talk, here's a webinar, and here's that scheduling model. And double-click that, and there's my model. And I double-click that, and there's my data. So I have some files here I can access right away. And now if I want to work with this, I can say here, model sched.mod, okay? And, whoops, oh, it's sched1.mod, 1.mod. And so, I got an error. So you click on this thing here, and it says, oh, there's an error, it's in that line. And require is not defined, and I see up here that it says, oh yeah, the parameter is called required. So I go in and fix that, and save that, and now I reset, and that, and now I can do data sched.stat, and I can pick Garobi, say, and now I've got to tell it, it's not in the data. What's the minimum number of people who can be assigned to any one schedule that I use? And I'll say I'll make that 11, and then I can solve, and Roby comes back and gets me some solution. And then I can display like how many people work each one. You can see that the smallest number here that isn't 0 is 11. And so that's basically how it works. I mean, we have some syntax highlighting to help you here, and keeps track of your files and so forth. And then so that's basically just what I wanted to show, is that this provides something, and it looks the same on all different platforms. So it's no longer true that someone who has a Mac say has to deal with something different than someone who has a PC. So let me go back here and say, so current version does. I've shown you all those things that it does, and we've done this as a partnership with an AMPL distributor called Optimization Systems, but we're going to be making this part of the AMPL product, basically taking it over ourselves. They have a fancier version that does some stochastic programming support, which is another whole story. And then later versions, I hope a lot of things will get added. So things to help you with options and so forth, and maybe access to the Neo server and various enhanced displays and so forth. And so hopefully we'll get some suggestions for that. Let me briefly show you something about Solver Studio. That's an interface from Excel. And so this is a quite different looking thing. The idea is to integrate algebraic modeling languages into spreadsheets and support a number of modeling languages, of which AMPL is one, and support lots of solvers. And this does have a Neo server connection. So Neo server is sort of a cloud-based selection of solvers that you can use for free. And it was actually started in the 90s when nobody had heard of anything called the cloud. But that's how we describe it today. And so Solver Studio looks like this, and typically you have in addition to all your regular Excel things, you have a little modeling menu up here, and you can have some Excel tables here, but you have a model here, and you can link the two of them. So you can, all your data for your model can be sitting in the spreadsheet, and you can change it in the usual spreadsheet way. And you can, here it's set, here's an example of the dialog that sets up the relationship between the parameters in the model and the ranges in the spreadsheet. And there's some description. So the big advantage of this is that the spreadsheet, you know, is this very sophisticated software. It'll do a lot of things for you, and that a lot of people like to work in. And the disadvantage is that when you get to really complicated data that has more than 2 dimensions or that's very large, then the spreadsheet sort of can get bogged down. And so it's not for everything, but it's interesting, and there's more information at solverstudio.org. So.
Bob, I just wanted to make one observation here. We have a number of people on the call here who are developers or you know, supporting modeling languages, you know, for other environments. You know, it seems like the Excel solution, you know, Solver Studio, that's more for those when you have a solver solution that you want to give to somebody, let's say a manager who's trying to work out shifts or something like that. And a lot of those guys aren't familiar with, you know, using solvers or other things, and so it almost seems like this is kind of a front end to allow less experienced users to use the use the solvers and the power of changing conditions and being able to re-optimize it. Have you found that that's mostly the case? Is with the Solver Studio, it might be for less experienced users or those who are trying to maybe deploy an optimization solution?
So it is one deployment possibility, and in fact, people are very passionate about spreadsheets, about how that's the way that their users want it to be deployed, and so it can be seen as both a development environment and as a deployment environment. And in the deployment environment, you could hide the whole model and everything, and just show the data. And it's good you brought that up, because in the remainder of the talk, I'm basically going to talk about deployment. And so this is sort of a transition from development to deployment. And whereas the IDE I showed is purely a development interface, this could be used as a deployment interface. And so what I want to describe are a couple other ways that people do deployment.
Yeah, I'd also like to hear, for example, from the TSU guys or John or others on their thoughts about this as well. About how we can take optimization solutions and maybe make them available to a more general audience. So anyway, I'm looking forward to
I think one thing that developers of modeling systems found was that anybody who had a real application needed to deploy it, and that the environment in which they needed to deploy it was generally quite different from the development environment. That if you're going to deploy it to a great extent, then it's going to be seen by users who are not going to know anything about the model or want to deal with it. Now that's not to say that there aren't some big users that are basically always in development mode, and that never really, there are groups of strategists at companies, and all they do is mine the model and sort of run it each month, and they don't really deploy it to additional people. But I would really, if we want to move optimization past that, we have to be able to deploy. So let me describe two ways now of deploying it in addition to the spreadsheet. Okay. And one is going to be by scripting, and the other is going to be by an application programming interface. Okay. So scripting is the older one. We hadn't really had AMPL in existence for very long before people started asking us to be able to write programs in AMPL. And the whole idea of AMPL was to get you away from programming, but then people came back and said, no, I want this interface. I mean, now that I have this modeling language, I want to be able to give a bunch of commands and tell it to write a loop over them, or to say, well, if this is true, then do this, otherwise do that. And then I want to be able to write this whole script and just run it as a batch thing and say, okay, run this script and have a loop over various solves and test various things and take action depending on the results and so forth. And so it wasn't long before we had to provide such a thing. So here are just a couple really simple scripts. You see in this script there's a repeat loop. It says repeat until the number of solves is equal to the max. Here I showed an example of a script, and you see how we had to put in like looping statements here. And you can loop over a solve. And when you change the data in the loop, it might actually change the constraints of the problem. In this case, a constraint automatically gets added every time I do this. And then when I run it, it goes through the loop, and each time through the loop, it calls the solver again and gets a different solution. So that's one simple script. Another one here is does the same thing, but using C-PLEX. In this case, I just set a bunch of options to tell C-PLEX that it should return a bunch of solutions, and then here I loop through them. So it reads solutions one at a time and displays them. And here you see another kind of loop where it indexes over a set. So you can actually loop over an index set in the modeling language. And so here we get the same thing, lots of solutions from the solution pool. And here's one more. This shows how you can do algorithmic things. If I take the same problem and I say that each schedule has to be worked by at least 19 people, if it's worked at all, it turns out it's a very hard problem. It takes like 41 million branch and bound nodes to solve this in almost 50 minutes of time. And in cases like this, you may think, well, why is it that I'm trying to make all my variables integer at once? I should really concentrate on which schedules I'm going to use and not worry so much about whether the number of people working each schedule comes out fractional, because so many people work the schedules anyway. And then afterwards, I'll fix the use variables and solve an easy problem to optimally round these fractional variables that say how many people work each schedule. And this is not necessarily optimal, but it turns out to always give the best solution. And it takes just a simple script to implement this. I mean, all you have to say is that we relax the work variables by setting this property of them to 1, the relax property. Then we solve. Then we fix these use variables, and then we set the relax property back to 0. So now they have to be integer, and we solve again. So you can write these sort of iterative schemes, these optimization schemes in there. And you see, I just include my whole script, and it solves once. Now it takes only about 1 million branch and bound nodes to solve that problem with a few work amounts that are 19.5 people, okay? But almost integer. And then I say, okay, these are the ones I'm going to use, and I ask it to now find the optimal integer solution. It turns out to just be 1/2 a person more than this, so in fact it is optimal, and I get an integer one. This only took me less than 2 minutes, and so there are also algorithmic things that you can do using these scripts. And now I've only shown a few simple ones, but to get back to what you were saying, people actually built very complex applications embedded in things using these scripts with many script files, hundreds of statements. We've seen ones where millions of statements are executed in each run. In fact, there was some statement counter that overflowed and had to be changed to a long integer at one point. And the application control is, however, indirect. That is, the application writes some data files for AMPL, and then it initiates an AMPL process that reads the script, and the script tells it what data to read, what solvers to call, what manipulations to do, and so forth. Eventually writes out some results. And when the AMPL terminates, then the application reads the results back in. So AMPL is still really a standalone system here, but by scripting it, it's possible to get it to do a lot of complex things that have been predetermined. And so from the application user's point of view, they're just looking at some application that was written in some other language with some other interface, and they don't even have to know that in the middle there, it relies on AMPL to run the model. And the advantage to the developer is that they still have the AMPL model there, and if they need to make changes, which happen over time, they can go back in and work with the model. And they don't have to take their whole model and turn it into C++ code or something like that. And so this has been used, like as I say, in a number of things in supply chain management and natural gas transmission. And we have a number of really big customers who do this kind of thing. And what we'd like to do is, and so there's a project now to try to improve these scripts by speeding up the loops. They can be quite slow because they're so general, especially if there's several nested. If there's a solve in the loop, then you don't worry about it too much because the speed of the loop is swamped by the time to solve. But if there isn't a solve in the loop, it can be slow. Another thing is to put in real functions. So right now one script can include another, but the idea is to actually have functions with arguments and return values and things that are defined locally to them, and then hook those up to the callbacks of solvers so that you could have a solver come back and call a function, and you could test whether the solution is good enough, decide whether to continue, that sort of thing. So we're still supporting scripting and trying to improve it. Now, scripting can only take you so far, however, and it does require writing these files back and forth and sort of showing out to this separate program, which is the AMPL. And if you're developing something in some other programming environment, then you can imagine that you'd like to get more direct access to what's going on in AMPL, so that you could really make a more integrated application. And that's the thing that we're we're developing now, and will be available for people to try this year, which is to do a real application programming interface for AMPL, which is, we've found is non-trivial because AMPL is not so simple itself. And the idea is to provide a callable library of routines that invoke various things that happen in AMPL. They give you access to all the parameters and variables and so forth, and they keep the modeling system active so that you can ask AMPL from your program to do one thing at a time. And so you can have your own loops, which within them do various AMPL things and which also do your own processing. And I'll show an example in a moment. And so this will eventually, the goal is to support what we see as the most popular programming languages out there, and also some of the programming languages that are used for analytics in particular, like MATLAB and R. And so unfortunately, of course, each one of these requires its own interface. They're going to be similar, probably all ultimately Java-based, but each one has its own wrinkles that have to be dealt with. And then from these programs, you'll be able to execute AMPL statements individually, read files when you want to, but also the important thing is you'll be able to exchange data directly. And so typically the big thing that's done in applications is to take the user's input and convert it and pull out the proper data. And the idea is you'll be able to send that data straight to sets and parameters, then invoke solvers and extract the results. And so all these things will be embedded within the applications logic. And so once the AMPL model is developed, it will not be necessary anymore to shell out to the AMPL application, be able to actually put this within your program. And so here's some examples. This is a file. This is a problem written in Java. You see that the AMPL environment gets created. It's possible to read files if you want to. And then there's this thing here that connects the variables that are in AMPL with program variables that are in Java. So you can have a program variable that corresponds to whichever AMPL objects you want to manipulate. And then you can run whatever AMPL commands you want. So you can run arbitrary AMPL commands, but you can also, after you've run a solve, notice I set the solver, ran a solve, and then you can get values back. And there'll be various methods to enable you to do certain things with AMPL objects without having to execute a whole AMPL statement. And then this thing finds a efficient frontier by looping over various solves. So you see that it does certain things that are Java commands and certain things that are AMPL commands. And it's inside a Java loop. So it's your program's loop. Okay? You're really controlling what's going on, and you're just referencing AMPL when you need to. Okay? And so this is a much tighter integration than the integration via scripts. And the idea is that if you're using something different, say MATLAB, I can do the same thing. So this is just what I showed you before, except in a different language. And the idea is a lot of these things will be the same, but some things will be different. Okay? So you can just briefly see here that I again interpret things, I again do solves, I again tie MATLAB program variables to AMPL objects, and here's that big loop again with the two solves in it. Okay? And in this case, it's a MATLAB loop, and it has MATLAB statements in it, and it has statements that reference AMPL. And at the end, you can do, say, a plot, and that's entirely MATLAB. Okay? Now, the key to all this is the data transfer, that you don't want to have to write like AMPL text data files out and have AMPL read them back in. You want to take data that's in a form that is natural to whatever programming language you're using, whether it's Java or MATLAB or something else, and push that into AMPL, and then have it do what AMPL do, what's the most natural in the modeling language, and then write various expressions for the data you want to get back and pull it back out. Okay? And so that's really what we're working on right now, is how to best do this. And you do want to be able to handle scalar data where you set a value to a set or a parameter, say, a value or get a variable value back. Like if you want to change one parameter value or something. But since models typically have huge amounts of data, you do not want to be sending one value at a time in some huge loop. And so what we've settled on is to use a table data structure to be the structure that's used to convey data back and forth. And partly this is because just about any expression you can write in AMPL gives a bunch of numbers which naturally are viewed as a relational table, with some columns corresponding to set members and other columns corresponding to different data values. And so it's very easy to take one of these tables and assign it to AMPL values, AMPL entities, or to create one out of AMPL entities. And so the idea that we'll provide a table object and then various methods to help in creating these tables. If you pull it out of a database, it's probably already in that format. If you have it in some other form, like in MATLAB, you might have a matrix, say, a two-dimensional thing, and there'd be some way that would just naturally, convert that into the form that's needed. And then you push that over to AMPL. And then when you've solved, you list the expressions whose values you want, and AMPL just makes those back into tables, and then there's some methods for extracting the data into the form you want. And so you can move the data back and forth, and that can all be handled by your program. And of course, a lot of the work of dealing with models has to do with data. And so it's possible to do that. And at no point do you have to write a file with a bunch of text tables or anything like that, the way you would do with scripting. Okay? And so that's what we're working on. And we hope to have the first two languages. In fact, I'm playing with them now and talking to developers, and we're making various changes and so forth. And so I think it's only a couple months before we're ready to send it out to people and ask them to try it out, with the idea that we'll eventually, later in the year, have it as a real release. It'll be part of the product. It's not a separate add-on or anything. It's just if you have a current AMPL, you can get the API, this API, and then the idea is to extend it to other languages with a similar structure, but modified for each language's particular features. And this is also something we're doing with Optimus, but it will be again, the idea is to make it part of the AMPL system, really. And so that brings me about to the end. I've gone from like interfaces that are just improving the modeling language, all through interfaces that help you deal with the modeling language, through interfaces that really let you embed it in other applications. And so I'd like to thank everyone for listening, and maybe open it to some more questions.
Okay, great. Thank you, Bob. Go ahead and unmute your microphone if you'd like, and or in the chat window if you have any questions. We have time for just maybe 2 or 3 questions if you'd like to ask those.
Okay, so I'd like to ask a question. This is Danielle.
Yeah.
Can you hear me? Okay.
Yeah.
So the question is regarding deployment again. You mentioned deployment in Solver Studio. I agree, because I mean, one thing is to use those languages for development and study. The other thing is to use them for deployment. So there's a whole new set of concerns that come in when you do that. Right. One of them, actually, I would like to find out about AMPL is if it's possible, instead of deploying a mod file, if there's any way to compile it into an executable or a binary file of some sort.
So I've been asked that. I don't expect that there's going to be something that'll let you just compile the whole model into an executable. That would be quite a different development project. What we're hoping is that this API will enable you to write essentially your program, which you can then compile, and then it will still need to access AMPL, but when it's running, but it will no longer be necessary to like have an AMPL script sitting around. or have an AMPL process, you know, that you have to fire up. But I think it's much further in the future to actually have something where you write an AMPL model and then somehow compile the whole AMPL script actually into executable code.
Okay, yeah, even if
quite
it's
a bit more difficult.
Yeah, even if it's just the mod file, like keeping the architecture of the separate, you know, model and data file would be fine, and the data could be.
Go ahead.
Open it to kind of build an executable
Sorry, Danielle, you got now.
That's static.
Yeah.
Okay, no.
So we have had people who want to. Go ahead.
Yeah, Danielle, I think your audio is cutting out, but
yeah. Anyway. So we have people who wanted to hide the model file, so we have ways of like encrypting it and hiding it there. It doesn't actually compile it though into code.
Okay.
And so it's a matter of some debate. Like, is the time spent, like, you know, interpreting the model file, is that really significant? Or, you know, or is the solve time really significant? And like, you know, it's enough that you be able to interpret it somehow.
And I found that if you really want to hide something from a user, all you have to do is just put it in the documentation, and it will be completely hidden. It's better than encrypting it. So great. Okay. So any other questions that we have? We have time maybe for one more question. Okay. So I just had Frank. You have a question? I thought you just.
Yeah. One more is a comment. The last company I worked for, I ended up interfacing C-PLEX to SQL because all the data was already in SQL. And I realized that the iLogs language OPL had some similarities to SQL. And so I'm wondering if maybe it might make sense to have a way of calling AMPL from SQL.
That's a good question. What we did in the past was the opposite. We made a way of calling SQL from AMPL. So there's a way of pulling data from an SQL database into AMPL things, and then also sending data back. And if you use SQL as sort of your application development language, then I guess that's something that we could consider, is whether you could do it in the opposite direction. So that
and it sounds like, you know, even if you did something with like Java can access, you know, it can do SQL calls and also AMPL calls. You might be able to combine those.
Yeah.
Okay.
Actually, yeah.
Okay. Well, great. Well, thanks, Bob, for the very great talk on, you know, the modeling interface and modeling language topics. I thought you did a great job of you know, making it interesting for those who are using AMPL, but also for those who are interested in you know, platform development or use. So I thought you did a fantastic job with that.